d squared Ca, not a capital, that's a material or full derivative. That will get into transport too. Minus the reaction rate times the concentration of A over the diffusivity of A through B. Alright, and we would like to non-dimensionalize our mass transfer equation with zeta. And this is going to be y over L. So just like I talked about the radius going from 0 to 1, this is going to start at 0 at the bottom of the tank. And then by the time we get to L, it's going to be a value of 1. We'll get L over L. So this is transforming our system to be 0 to 1. And now I don't care necessarily how long the system is. It's just either I've made it 50% of the way through, or I've made it 100% of the way through. We'll also choose, and this is very common to choose, a chi. So I wrote this out. I was when I write on the chalkboards and things, sometimes it's hard to tell what I'm exactly writing. Is it X? This is a chi. So we'll use chi being the concentration over the original concentration. Remember, we called the original concentration was the partition coefficient multiplied by the feed stream concentration. Chi is going to be concentration as a function of y. All over KQCA. So let's see, if we look at this, at y equals 0, we actually have KQCA naught. So chi is going to go as we travel up the system. Chi is going to go from 1 to 0. So we have Z or zeta going from 0 to 1. As chi goes from 1 to 0. And I think we can start here and then we can go back to the thermal portion of this. So we need to make use of the chain rule here. What we'd like to do is transform this system from being a gradient of concentration with respect to y and being a gradient of chi with respect to zeta. So let's go through and figure out how to non-dimensionalize this term. I'm going to write this, I'm going to split it back out into two first-order derivatives. So taking the second-order derivative is the same thing as saying I'm going to take the derivative with respect to y of the derivative of Ca with respect to y. So I need to transform this into the derivative with respect to zeta of the derivative of chi with respect to zeta. That's what I need, but like we looked at the color and the temperature, I can't just make this substitution and be satisfied in what I've done. I need to make sure that as I'm making these changes, my mental check is I make sure that this is mathematically true. So I have dd zeta, but this used to be a ddy. So I needed to multiply this by dy d zeta. And now, for this, that will get me a ddy. Actually, I just needed to have a 1 over d zeta there. So this is going to be transformed into, if I wanted a d chi d zeta, I needed to multiply this thing by dy d zeta and a d chi dCA. And I also said another dy d zeta. All right, I'm not going off the page. And my mental check is going to be this. If I go through this half of the equation, oops, I did this completely backwards. So what I would like to do is, it's going to be d zeta, dy, this is going to be dCA, d chi, this is going to be d zeta, dy. Yes. All right, because my mental check for myself, what I was just looking at was, I want to make sure that if I cancel these things, actually yellow's not going to show up, but if I cancel these things, d zeta, d zeta, d zeta, d zeta, d chi, then I want to make sure what I end up with over here is the same as what I started with. d dy, d dy, dCA, dy, dCA, dy. All right, so I just did this all backwards. As soon as I went to start canceling things, they weren't canceling for me, and I realized I did this wrong, and I needed to actually write it like this, and now my mental check works. d dy, dCA, dy equals d dy, dCA, dy. So this is what I need to solve.